Right. So far, this has been our progression. So first we started with, I think cadence. First, what we have done was understanding what you saw. Okay. So we have seen that it is a very involved tool, commercial tool, which has a lot of capabilities. We tried to understand its capabilities. So fundamentally, what are those capabilities that were useful to us? It gives us access to small signal parameters. Okay, so you know that big drop down that comes out from which we select those small signal parameters, right? GM, GDS, CGS, CL, all those things. So all the access to the small signal parameters. And also it has a very good calculator. Okay, so from which we can form expressions. So if you wanted to form 20 log mod V naught by V1, so we were able to do that. If we wanted to form GM over ID, okay, so then we were able to do that. Or if we wanted to form an expression like GM divided by GDS, we were able to do that. So we have a very good calculator which was able to form expressions. And a very good feature was wave versus wave, if you remember. Suppose I wanted to plot GM over ID versus the intrinsic gain GM over GDS. Then we exploited the wave versus wave feature, and then we were able to plot. So that was the introduction to cadence lab that we have done. In the next lab session, what have we done? Okay, so I tried to convince you that GM over ID methodology, it gives you access to a solution space. Okay, and from this solution space, why only this GM over ID? And there are some other terms, right? GM over ID. So ID by W, GM by GDS. If I talk about any bandwidth related, so I think GM by CL. Okay, so the unity gain frequency, all those come into picture, right? So all these, what are these parameters? What is the uniqueness of these parameters? What is the uniqueness? Instead of purely considering GM ID, okay, GDS in a standalone way, CGS in a standalone way. If I consider these parameters, what is the advantage that I have? These parameters are what? These are what? Nobody remembers? These are independent of what? Width. Okay. So we have seen that the solution space can be created readily. Okay. So if you are considering these parameters, okay, so this becomes uh, nested for loop, and the depth is 4 almost. 4 nested for loops. If you consider these parameters, your simulation becomes very, very easy. So this is also a nested loop, but 2 for loops. Okay, one for loop within another for loop. So the solution space can be found out very easily. So we had a good discussion and derivation, and I tried to show how these are independent of width, and that discussion we had. So in this class, what we have done, we have um, sized a common source amplifier with resistive load, just as a proof of concept of whether this method is actually working or not. Then in the last lab, okay, a previous lab, we have sized common source amplifier with active load. Okay, so yeah, if we look at it, lab 4. Yeah, so what are some of the, yeah, so what happened? Okay, we basically derived the transfer function again. So what we have done today, Okay, and we had to derive that in the previous class itself. Of course, today it would have made much more sense because we had the same discussion. So the numerator polynomial, denominator polynomial, whatever we discussed today, the same thing, and the pole frequency. Okay, so all those things we were having the discussion, and the Bode magnitude plot, Bode phase plot. Okay. And then we calculated the unity gain frequency as well, minus GM1 by GDS1 plus GDS2 plus SCL. The mod, we made it equal to 1. And we know that mod A plus JB is under root A square plus B square. We substitute that. And then we found out the unity gain frequency is GM1 divided by CL. So that means the unity gain, this is radians per second. And in hertz, it will be 1 by 2 pi GM over by GM by CL. Okay, and today we have actually seen that, or in the last class, we have seen biasing circuits where the biasing is done with the help of current sources. We have discussed the current mirrors. So this is the most basic current mirror, but the PMOS type. We discussed the NMOS type. It is exactly the opposite. So all the NMOS transistors will be stacked from ground to up. Of course, the PMOS will be stacked from VDD towards the ground. Okay, so this is the basic PMOS current mirror. So whatever is the IREF here, the same IREF flows through this one as well. And then we did the simulation. So we found out the different values for, or we found out the W by L values for the given requirement. Okay, so today what we shall do, anyways, we already discussed the differential amplifier with the current mirror load. So today, I think this is lab 5. We will discuss differential amplifier with active current mirror load. Okay, what we discussed in the morning class, the same thing that we will size it, and we will see the simulation. Okay, so we had this discussion in the morning. This is V1, V2, M1, M2, M3, M4. This is my VDD. And this is a current source. What is a current source again? What is the current source replaced with? What will we have here? Yeah, so this is the circuit that we are trying to size. And let this be V out. Let this be V out. Okay. Right. So how do we proceed? Any ideas, anyone? Where do we start? Where do we start? Where do we start? Where did we start for this one in the previous lab? Where did we start? So we took a spec. Okay, so let us design for the same spec. Okay, so design a common source amplifier, or this thing will change, of course. Design a diff amp with active current mirror load. So I want a minimum gain of 10 V by V. And what is this? FU stands for what? We have seen it in the Bode plots. What does FU stand for? What is this?
Unity gain frequency.
Yeah, unity gain frequency in hertz. The frequency at which the magnitude is equal to 0 dB or 1. Okay, so that is the unity gain frequency. And this is the load capacitance that I have at the output node, which is 1 picofarad. So let me introduce the load capacitance as well over here. So this is what I have. This is what we have. Okay, so let me call this M5 and M6. So where do we start? Where did we start in the previous lab? What did we calculate? Where did we start? Okay. What all did we calculate first? So we calculated omega u and fu. Okay. So all this came from what? All this came from this one. What is this called? What do we call this?
Transfer function.
Transfer function. So for the given circuit, you have to calculate the transfer function. That is the starting point, right? Yes or no? Okay. Now tell me what is the transfer function of this one? So you know that M1 and M2 are matched. M3 and M4 are matched. M5 and M6 are matched. Okay, so if you want I out to be Iref, okay, so this I naught, let it not be I out. So let me just call it I naught. If I naught to be Iref, then these two should be matched. M5 to be M6. By matched, I mean they'll be having the same dimensions. Okay. Now tell me what will be the transfer function of this circuit? What will be the transfer function of this circuit? Anyone? So I'll give you a small hint. Today morning, I derived a lot of stuff. Okay. So what is the DC gain of this amplifier? Okay. Is it giving any idea? Yeah. So this also we discussed, right? So from this, what can you say? So the transfer function over here is CL. So what will the transfer function here be? V out by VD, the differential gain anyways. Yeah. What will this be equal to? Is there any difference between these two? What is the DC gain? See? Minus GM R01 parallel R02. Here also DC gain is what? See that what is the DC gain? GMN parallel RON parallel ROP. Okay. So what is the only thing that got added extra? CL. So the only thing that got added extra is CL over here. So will the transfer function be any different or will it be the same? It will be the same without GDSP plus GDSN plus SCL. Yes or no? Do you agree with me? I went through. So I gave you the basic KCLs, right? And then three important equations. From these three important equations, we did some substitutions and we ended up with the DC gain almost equal to the same as the common source amplifier with an active load. Okay. So this common source amplifier with active load, I redrew as something like this. Okay, and the differential amplifier with current mirror load, I redrew as something like this. Okay, so both are having the same DC gain. Okay, both the common source amplifier with active load, differential amplifier with current mirror load, both have the same DC gain. Now what I'm adding extra, I'm just adding the load capacitance extra over here. So will both not have the same transfer function? Yes or no?
Yes, sir, they'll be same.
They'll be same. Are you convinced? Okay, so you need not do the entire math. It will come out to be exactly the same. It will come out to be exactly the same. Okay, right. Now how can we proceed? We can proceed in the same way that we did for this one. Will it be any different? Will it be any different? It will not be any different, right? So what is Fu equal to? 1 by 2 pi Gm1 by Cl. So what will be Fu over here? What will be Fu over here? Will the derivations be any different?
No, sir.
Okay, they won't be any different. So that is the advantage. Okay, not advantage. That is a good insight that we can draw from whatever we have derived in the previous class, in the morning class. Okay, so what is the DC gain? Will it change? Will the DC gain change? Okay, so let me write down the transfer function here itself. Okay, so this is just GMN. So why I am writing GDS? What is the reason I'm writing GDS? So the tools give you access to this term GDS. That is the only reason we are writing it as GDS. Even both Cadence and LT Spice, they specify the small signal parameter GDS, not RDS. That is the only reason we are writing it in terms of GDS. Okay. So will the derivation be any different? Will the derivation be any different? The GM over ID methodology, will anything change? That is the question that I'm asking. So how did we proceed? DC gain, we wanted GM1 by GDS1 plus GDS to be equal to 10. Okay, I assumed, or rather we assumed GDS1, GDS to be equal to some GDS. So GM1 by GDS became equal to 10. So that means GM by GDS should be greater than 20. We took a value of 25. Okay, it can be anything 30, 27 or anything. So we just took an assumption and we made it 25. So from this we calculated FU, or rather we calculated GM. Okay, so FU is 100 megahertz, that is already given. So if you substitute things, I got the GM as 628 microsiemens. So from GM1 we calculated GDS. GDS is nothing but 628 divided by 25, because we assumed that GM by GDS to be 25. So we calculated the GDS also to be equal to 25 micro. Okay, so then what did we go ahead with? So we went ahead with GM by GDS versus GM over ID. Okay, and then we calculated the widths of several things. So that is how we proceeded, right? So will the sizing be any different? What all sizings did we get? So M1 to be 1.5 micron. Okay, and M2 to be 15.5 micron. M2 and M3 are matched devices. So M3 will be 15.4 micron. Okay, so IREF we got as 128 microamperes, but that IREF gets doubled. So what is 128 times 2? 256. So it becomes 256 micron. Yes or no? Okay, right. Are you getting the picture? So what I am trying to say? So what will this be equal to? What will be the size of M1, M2? Anyone? What will be the sizing of M1, M2? What did we get here? M1 as 1.5 micron. Are you able to follow? Yes or no? So all I'm trying to say is both circuits are exactly the same except for the tail current source. So this one has a current source over here, but this one has a tail current source or is a source current source node, as they say some textbooks. Okay, so this IREF will be exactly the double of whatever IREF you calculate over here, because you know that this is I naught by 2, this is I naught by 2, total I naught will flow here. So if we got 128 micron here, you will get 128 into 2. So this IREF will be equal to 256 micron. Okay, so that is when what will be the current through this one? 128 micron here and 128 micron here. What was the size of M2 from this lab? The same procedure. Sorry, M1, 1.5 micron. So you'll be doing the same thing over here. So W2 is 1.5 micron. W1 is equal to 1.5 micron. Okay. And see what is M2, 15.4 micron, M3, M4 are matched. So W4 is 15.4 micron. W3 is also 15.4 micron. Okay, what else is left out? So we have to give some input voltage here. So that differs a little. Okay, so this V in, how much V in did you have to apply? Did we calculate the V in that we have to apply? So GM over ID versus VGS. Okay, so we calculated it to be around 800 millivolts, right? Yes or no? So we calculated it to be 800 millivolts, but it cannot be 800 millivolts here. Why? Because so that VGS or the voltage that you are going to apply here, the common mode voltage. So it should be from the gate to ground. Okay, it should be from gate to ground. Okay, but you got only this value. VGS is 800 millivolts is what you got. Okay, so it has one more drop over here because this circuit is slightly different in the bottom part. The previous circuit, this node is connected to ground, but this circuit is not connected to ground. It has another current mirror over here. So what I am saying, so there will be some drop here as well. So that drop also should be added to this VGS, and this will be, this common mode voltage will be that particular voltage. Okay, so that is a small difference. So this will be 800 millivolts plus some voltage. Okay, so let me assume a overdrive voltage of 200 millivolts here. Let me assume a overdrive voltage of 200 millivolts here. Okay, so that means 800 milli plus 200 milli. So this becomes 1 volt. So the common mode voltage that I'm applying is almost 1 volt over here. Okay. Right. Now we are left with sizing M5 and M6. Any ideas how to size M5 and M6? The sizing of all the other 4 transistors is very, very similar to the previous circuit, right? Because all the spec, everything is the same. Okay. And the small signal picture of these two is exactly the same, that we have taken a lot of pain and we proved that mathematically also we have proved that both are the same. Now tell me, how do we size M5 and M6? Okay. So what is the overdrive on M5 that we are assuming? Is
100
200
milli.
milli. Okay. So we know that what is V overdrive equal to VGS minus VTH. So from this, what is VGS equal to? V overdrive plus VTH. So this overdrive is 200 millivolts that we are taking an approximation. So this VTH, if this is connected to ground, I think it is 498 milli or 500 milli. So from the curves, you can get that. So this VGS is how much now? 700. millivolts. 700 millivolts. Now what curve shall I look for now? So for M5, what is fixed now? What did we fix? We want a
VGS.
VGS. We want a VGS of how much? 700 millivolts. Okay. So what is the curve that comes to your mind? So what is the first curve? GM over ID versus VGS, right? So from this curve, what will I obtain? So I already have the VGS value. From this curve, what will I obtain? I obtain the value of GM over ID. Yes or no? This is for MOSFET 5, M5. Okay. So once I have GM over ID, what is the curve that I will look for now? GM over ID versus ID by W. Yes or no? Okay. So what is the ID that is required here? This is 256 microamps. So from this, you can directly calculate the W value. Yes or no? Do you agree with me? From this, can I directly calculate the W value? And M5 and M6 are matched, right? M5 and M6 are completely matched. So whatever W5 will be equal to W6. Yes or no? Do you follow? Did you get the picture? Overall, did you get a bird's eye view at least?
Yes, sir.
Okay, right? So the design is complete, sir, no?
Yes, sir.
Okay, so let us simulate this. 1 second, please. Another computer, I'll get this. Yeah, am I audible?
Yes, sir.
Okay, yeah. Let me share my screen. Yeah, are you able to see my screen? Right. Okay. So do you see it is the same circuit? Okay, so this one I got 1.5 micron and this one I got 19.5 micron. So this current, each branch current I got 117 micron. So that is why this became 234 micron. Okay. And M5 and M6, the sizing was similar, whatever I discussed earlier. Okay. And then I am doing an AC analysis. So if I run it, okay, so I need to plot the output over here. Okay, so I got the output. So what is the gain? What is the DC gain? Look at the top beside that hammer. So you can see the DC gain is around 23.3 dB. So is it above 10? 23 dB, is it about 10? Can one of you calculate what it is in V by V and can you see if we are meeting the spec or not? Okay, so the 0 dB somewhere here. Yeah, we are almost there at 100 megahertz. It is minus 1.3 dB. We are missing it by 1 dB or we are missing it by minus 1 dB roughly. See, at 100 megahertz, it should have been 0. But we are getting around minus 1 dB. But that is fine, I guess. We are almost there. Minus 1 dB, we have 99 or 100 megahertz thing, which is permissible. Okay, do you see both unity gain frequency and the DC gain both are satisfied? Yes or no? Okay. Convinced how to size all the transistors? So if you have followed the previous lab, this would be an extension. Only thing we are sizing is these four. The sizing of these four is exactly same as whatever we did in the previous lab class. In this class, we sized only this one. Okay, that too we assumed some 200 millivolts here. And mind you, that 200 millivolts you are supposed to add to this one. So previous class, I think we got 0.78. So that 0.78 plus 200 millivolts, VGS plus 200 millivolts is the total voltage of the input common mode from this node to ground. Okay, so that is why we have to add this 200 millivolts extra to this. Okay, so this becomes 0.98. So if we look at the spice error log, okay, if you look at M1 and M2, see M2 is here. M2's GM is 587 micron. There is a slight difference. What was the design value? For 625 microns, right? The design value is 625 microns. See M5, current through M5 is this current mirror. Current through M5 is 234 micron, but through M6, where is M6? It is 183 micron. Okay, and 183 divided by 2 will give me some 90 point something, 91.3. Okay, so because the current is reduced, that is why we have a reduced VGS. Sorry, we have a reduced GM. Okay, see here the current got reduced. Ideally, it should have been 117 microamps, but we got only 91.3 microamps. That is why, because M1 and M2 in this configuration, they do suffer from, what do these two suffer from? M1 and M2. M1 and M2, which second order effect do they do these two suffer from?
Body effect.
Body effect comes into picture, yes or no? Because the substrate is at ground, but the source is at 200 millivolts, right? So VBS comes into picture. When VBS comes into picture, VTH changes. Okay, so whatever we have assumed VTH to be an ideal value, right? 500 millivolts, that would have changed. So let us look at that. What is VTH of M1, M2? So if you see M2 here, so there will be VTH. See, what is the VTH of M2? Because of the body effect, it is almost how many millivolts? 540 millivolts, yes or no? So the VTH changed. So if you look at M5 and M6, the VTH is almost very near to 500 millivolts, 498 and 494, very close. But the almost 40 millivolt variation is there for M2 and M3. The same thing will be there for M3 as well. Sorry, M1 as well. So if you look at M1, M2, both are the differential pair, right? See the same value, 540 millivolts here. Okay. So because of these differences, that ID got reduced, and because of the reduction in ID, the GM got reduced. So that is the small variation that you see over here. So if I want to increase the GM without thinking about anything, okay, so I can make this some 1.04. Okay, so this is a bad way of doing things, but still I know that increasing the input common mode will increase the gain. Okay, so you can see the gain seems to have increased a little, but let us look at the spice error log. That will give us a better picture. View spice error log. Okay. Yeah, so this is much better, right? 96 microamps. So previously it was 91 microamps. Okay. So, and then if you look at the GM also increased. It was going to the ideal value. So we got 628 microsiemens. We are almost there, 592 microsiemens over here. So it is a better design compared to the other one. Okay, the previous values, of course. I did it in a very non-scientific way, which is called as spice monkeying, because we have the spice tool. We almost have that tendency to change few things here and there and check the result without thinking. So that is called spice monkeying. Okay, so don't do spice monkeying. So understand why this current got reduced. Okay, in order to increase this current, what is a better way in which we can increase this current? We can have a better current mirror, right? Okay, so what is the better version of this current mirror? So all I am saying is this current mirror is prone to the node voltage here. And if you, sorry, if you want I reference to be equal to that I out, what all should be equal? So if you want I out, this output current to be equal to I reference, what all should be equal?
VDS and VGS.
VGS and VDS, but this is more prone to the variations in VDS, right? Because end of the day, these two act like source followers, and whatever is the variation here, it comes over here as the average of these two. Yes or no? We have seen in the morning V1 plus V2 by 2. Yes or no?
Yes.
Okay, so this node is prone to lot of variations from the input side. So how can we better this? How can we better this from the previous lecture? This I want to replace it with
Cascode.
cascode. Yeah. So let us go and do that cascode arrangement. So I have done that already. Different windows are opening up. Okay. Right. What do you see over here? What cascode did I? So this is same. This is the same exact thing. All I changed is this particular arrangement. What is this particular arrangement? What is this current mirror called? So this is low voltage wide swing cascode, right?
Yes.
Sir, no, we have seen that. And this is VG. Okay, so so how do we bias this? We again go for a resistor over here, and then we have seen in the theoretical class again. Okay, right.
Yes.
So yeah, how do we proceed? I want to size this current mirror. I want to size this current mirror. How do we proceed? What is the assumption that we make?
Overdrive.
Huh?
Overdrive.
Yeah, overdrive. Suppose I wanted 200 millivolt overdrive here. That was the assumption that we did in the previous class as well, right?
Yes.
Yes or no? This at this point I wanted a 200 millivolts overdrive. So now also I'll make the same assumption. I wanted 200 millivolts overdrive over here. Okay. So I'll split that equally. So 100 millivolts for this and 100 millivolts for this. Is that fair enough?
Yes.
Okay. Now if the overdrive of M6 is 100 millivolts, what will its VGS be? VGS is 1 overdrive plus VTH. Yes or no? And this is nicely connected to ground, so the VTH will be ideal at 500 millivolts. Okay, so what is VGS of this one? See, we know that overdrive is VGS minus VTH. So from that I am telling VGS is nothing but V overdrive plus VTH. So V overdrive, I am assuming 100 millivolts overdrive over here, and I know the VTH of this MOSFET is 500 millivolts. So what is the VGS of this MOSFET? What is the VGS of this MOSFET? VGS is V overdrive plus VTH. Okay, so this overdrive is 200 millivolts. So from this point to ground is 200 millivolts was my assumption. So that I split 100, okay, 100 millivolts and 100 millivolts. Okay, so I'm telling the overdrive of M6 is 100 millivolts. Okay, and VTH of M6 is 500 millivolts. So what will its VGS be equal to? What will its VGS be equal to? Yeah, not understanding. Yeah. What will the VGS be equal to? I told overdrive is 100 millivolts. Threshold voltage of this M6 is 500 millivolts. So what is VGS equal to?
600.
600 millivolts. Yes, fair enough.
Sure.
Okay. Now which curve will I refer to? Which curve will I refer to?
GM over ID versus VGS.
GM over ID versus VGS. Very good. So from that curve, what will I obtain? GM over ID. Okay. So after that, what curve will I refer to then? Okay. Anyways, let me open the MATLAB as well. I think you are having a hard time to visualize. Okay. So yeah. Okay. It is loading. Yeah. So I'll go to my NMOS browser. So I want to look at GM over ID versus VGS. What is the VGS value? 600 millivolts, right? So yeah, at 600 millivolts, what is the GM over ID value? So even better, can I get? Yeah, 600 millivolts. This looks fine. Yeah, 13.8. Can you see that? At 600 millivolts, what is the GM over ID value? 13.8. Now I go to GM over ID versus ID by W. So my length of interest is 180 nanometers and GM over ID interest, the value that I'm interested will be 13.8. Where is 13.8? 13.8. Okay. So what is the ID by W value here? 14.75. Can one of you help me? What is my ID here? What is my ID here? What is ID here? 234 micron. The same thing I want to flow through here. Okay. So ID is 234 micron. ID by W is 14.75. So what will W be? Can one of you help me? Understood, right? So at GM over ID of 13.8, I have a ID by W of 14.75. Okay. So ID by W is 14.75 and my ID is 234 microamps. So what is W? 234 micron divided by 14.75. Anyone? What is the value?
15.86 micro.
15.86 micron. I think I gave some 15.4 anyways. Let me give the same 15.86 micron. So these two would be identical. Yes or no? Okay. Now I have to size this one. I have to size this one. Okay. What is the overdrive? What is the overdrive? So
100.
here I assume 200 milli. I spend 100 millivolts here. What is the overdrive of M8?
100 millivolts.
100 millivolts. So everything will turn out to be the same. Yes or no? But this suffers from what?
Body effect.
Body effect. So that VTH, okay, we don't know because that body effect depends on how much potential this source node is at. Okay, but we go ahead with that VTH value 500 millivolts and we see that we get the same values, right? So 15.8 micron and 15.8 micron. Yes or no? Okay. And what is this value VG? From the theory, if you remember, I calculated this to be 2 overdrives plus VTH. Yes or no? This value VG should be minimum 2 overdrives plus VTH. Okay, so 1 overdrive is 100 milli, 2 overdrives is 200 milli, plus VTH is around 500. So I added some body effect. Okay, so 0.72 something extra I added. Okay, so that's why I took 0.72 over here. So is the sizing clear? 15.8 over here. So 15.8 here, 0.72 here. Okay. And then the same. So whatever VGS you get 0.8. Oh, sorry. This Mac keeps coming out. I think it is out of RAM or something. Okay. Yeah. So this is the 0.8 plus 200, 220 or 230 millivolts that we add over here. So that is why it came to around 1.2. Okay. So let me run this. Okay. So what is the DC gain that I'm getting? At 10 Hertz, almost DC 20.14 dB. I think it is greater than 10 V by V. What is the unity gain frequency I am getting? Or at 100 megahertz. Okay, I'm almost there. Minus 500 milli dB is 0.5 dB. A 0.5 dB variation I think is acceptable. Okay. So let us look at the error log. Okay. See, this is M6 and M8. What is the current through M6? See, this is 2.2 or 223 micron. This is 234 micron. Okay. So these two are almost the same. See, are you able to see? So M1, M2's gain or transconductance should be 628 microsiemens. Okay, so these are the values for M1 and M2. So almost there, 610 microsiemens. We are almost getting there. Are you able to convince yourself that this is a better design? What was the value that we got here? In this branch current, I think it was somewhere around 180 microns, right? In the previous design. So what do I mean to say is in this design, okay, so if I look at the error log, okay, I didn't run. I don't want to, I just want to see the spice error log. So I want to check M6, the drain current through M6. So the drain current through M6 is C 192 microamperes. But what is it supposed to be? It is supposed to be 234 microamperes. Yes or no?
Yes,
Are you
sir.
able to see? Yeah. So this is a much better design. Are you able to see? So let us look at the current through M8 or M6 because both are in series. And let us look at the current through M5 and M7. So how close or far are they from the previous design? Okay, so if I look at it, see this is 234 micron M7. Okay, and M6 is 223 micron. So you are almost there. Yes or no?
Yes.
Very, very faithful copying of this current. Almost. Yes. Are you able to follow? So this entire thing, this remains the same. Okay. So whatever we got in the previous class, the same thing I wrote. Okay. Is that clear? But is this allowed? Do you have ideal voltage sources on an IC? Is this allowed? This is not allowed. What? How did we replace it with? So this VG, we got it from R. I connected an R here. On the top of the R, we wanted 2 overdrive plus VTH. On the bottom of the R, we wanted 1 overdrive plus VTH. Do you remember? I think the last class. Yeah, the same thing. Yeah, see this point is, what is this point? We want 2 overdrives plus VTH. And this node is 1 overdrive plus VTH. Okay, so the drop across the current, the drop across this resistor is 1 overdrive. So 1 overdrive is what we calculated to be 100 millivolts, right? Okay, and the current through this resistor is 234 microamps. So what is the R value? R is equal to V by I. V is 100 milli divided by V is equal to IR, R is equal to V by. So 100 milli divided by 234 microamps. So what that will give some value. So that is how you calculate R. Okay, on top of this resistor, we wanted 2 overdrive plus VTH. At this point, we know that it is 1 overdrive plus VTH. So the voltage drop across the resistor is 1 overdrive. So 1 overdrive we calculated or we assumed it to be 100 millivolts here. So R value will be V divided by I. V is 100 millivolts. The current through the resistor is, okay, 234 microamps. So 100 by 234 microamps. So it gives me something. So that is the value of R. Okay, so let me open that as well. Think I did it as this one. Okay, right. So this is supposed to be R. Okay, but that R, how do we get this R? What was our discussion in the previous class? That resistor, we all We all knew that resistors are not allowed, or it is difficult to fabricate bulky resistors. So it is better to go ahead and replace that resistor with a NMOS that is biased in which region?
Linear
That is
region.
deep triode region. So that is why I connected the gate to VDD itself. Okay. And then, okay. So now an important question. Now, can I use these curves to size this MOSFET M9? This is M9, right? You can see the name M9. Can I use the curves that I gave you, the MATLAB curves that I gave you to size this particular MOSFET? Okay, all those curves we got. Okay, that was
This
for
one
the
is a
MOS.
linear region.
Yes, very good. So all the curves that we got was for the MOSFET in which region?
Saturation.
Saturation region. But this MOSFET is in which region?
Linear region.
Linear region. So we cannot use those curves. Okay, we cannot actually use those curves. What you can do is, you know, these voltages. So what is this voltage? 2 overdrives plus VTH. Yes or no? Yes or no?
Yes, sir.
This is
Yes,
1
sir.
overdrive plus VTH. Okay, which is 100 milli plus 500, 600. This is 700. So connect two voltages, 700 millivolts here, 600 millivolts here, and this is connected to 1.8. Now change the W and see at what width you are getting the drain current to be equal to 234 micron. Am I making sense? So this is an extra step that you have to do, because all the curves that we have taken are for the MOSFET that is in saturation region. But this has slowly, we know that this is a MOSFET that has to be operated in deep triode region. So what I am saying is, you know VG, which is connected to VDD. You know its drain voltage is 2 overdrive plus VTH, which is 700 milli. You know its source voltage 1 overdrive plus VTH, which is 600 milli. So now take another schematic. So take an NMOS, connect VG to be VDD 1.8 volts, connect VD to be 700 millivolt source, connect VS to be 600 millivolt source. Now play around with the width and identify a value of width for which the current is exactly equal to 234 microamps. Am I making sense? Okay. So, or you can do some, what do you say, guesswork, like I told, spice monkeying. Okay, you can, but in the spice monkeying also you use some of your brain. So based on those values, you either increase or decrease. Okay, whichever is more intuitive to you, you can follow that. So let me run this. Okay, so yeah, it looks familiar, looks similar. 22.8 and at 100 megahertz. What do I have? Yeah, minus 0.3. Yeah, minus 0.5 milli dB, or fine, minus 0.4 dB. 0.4 dB variation is allowed because this is a log scale. Okay, I think it is not much of a problem. Okay, so yeah, now let us look at the spice error log. Okay, right. See, this is carrying 234 micron M7. M8 is carrying 207 micron, so it has deteriorated a little. Let us look at M1 and M2 GM. M1 and M2 GM is 605 microsiemens, but in the design we got 628 microsiemens. Okay, so we can improve that. Again, don't follow me. Okay, so I add some 200 millivolts here, 1.2. Okay, so you should have. Oh, something is wrong, always coming out of screen sharing. So if I look at the spice error log, oh, okay, some disk space problem is there. Yeah, so this is much better. See, 234 micron, 224 micron, almost very, very faithful. Okay, very faithful this thing. So M1 and M2 are my input pair. Let us look at GM. 607 micron, close to that 628 micron that we were planning. But you can see the current mirror is very much better current mirror over here. Very small variation. Okay, so let us plot the AC response as well. Okay, so the DC gain is around 22 dB and the unity gain frequency are at 100 megahertz. What is happening? 100 megahertz. Yeah, it is much better. Previously, it was a minus 0.5 dB. Now see, because GM increased, see the unity gain frequency is GM by CL, right? CL is a constant. GM is the one that we are varying. Okay, so it is minus 0.3 dB. So much better compared to the previous case where we had minus 0.5 dB. We improved it a little. Okay, but that's fine. Minus 0.3 dB variation is not that big variation compared to 0 dB. So it looks fine to me. Okay. Is that clear how I sized all these? Is that clear? Yeah. Right. You can try with this. This will be the last experiment. Okay. So I will upload lab 4 and lab 5 assignments as also in Takshila portal. Like I told, I'll give you 1 month. So today is 18th. So 18th August, you will have the deadline. And then we can close the labs. Okay. Yeah, I think the correction is also done. The TA has finished 4-5 days ago itself. You might get the marks anytime soon. I don't know. The exact date, I don't know. You can go through the scripts and if you feel the verification was not fair or just, you can apply for revaluation there itself. Some revaluation window will also be there. Okay, as soon as I get that information, I will pass it on, or you might also get receive direct mails regarding that. Okay, so yeah, are you able to follow what is happening
Yes, sir.
today? I think there is much lesser enthusiasm. I don't know why. Maybe I should. Maybe I should try different things to excite students. Let us see. Maybe next class I'll come up with something. Are you able to follow morning's class and with today's lab? If you feel something is going in a wrong way, you please let me know. We can work it out if you want a different kind of delivery, or if you feel something is a little boring and all, we can decide upon the path to take so that all of you will be involved in the delivery.
Hello.
Yes, please tell.
Sir, so far you have added the two more lab assignments. One
Ah,
is with respect to NMOS, PMOS,
ah,
and the other one is for common source amplifier
with a
with
resistive load. Yeah.
resistive load and GM over ID methodology
Yeah.
topic. And
Yeah.
along with that, you are saying two more will be added, right?
Yeah. Last class and this class.
These two will be added. Okay,
Or
understood. Understood.
only one. I think only one.
Mhm.
Uh, what did we do in the last class? Losing my brain. So this lab, have I given the lab for this one? I think I gave this as lab 3, is it? Is it not?
Lab 3 was, just a minute.
Common source amplifier with an active load. Can one of you please check?
1 second, 1 second. I'm just checking that. Yeah, lab 3 is design a common source amplifier with a resistive load
Ah,
for a given voltage gain and frequency of 850 megahertz.
okay, okay, okay.
Like
So
use
this
GM
will be
over ID
lab 4.
methodology.
This will be lab 4.
Okay,
And today's class will be lab 5.
lab 5.
Ah,
So all these labs combined with the actual classes would
ah,
be the EC1 unit comp marks. Am I right?
So the labs, I think I have marks for 20 marks. Okay, so 15 for lab assignments, 5 lab assignments, right? 5 into 3, 15, and there will be lab exam online only. So based on lab 3, lab 4, lab 5.
Okay.
Okay, and it will be LT spice based, that will be 5 marks. So 15
Okay.
plus 5, 20 marks is done in EC1. Okay.
So all other quizzes will
So
constitute for another 10 marks.
as another 10 marks. So I have given multiple quizzes, right? 3, 4 quizzes I have given
That's
already.
correct. Four
Okay.
quizzes per annum.
Either I will take the best of them. Okay.
Mhm.
Or you want me to take the average, I will take the average. Okay.
Mhm.
So based on that, I'll give the other 10 marks.
Okay, understood. Understood.
That will
So,
be.
and there's the another point which I wanted to talk to you is you just mentioned a few minutes ago that we can see our mark sheets evaluated, right?
Yeah.
So this is in the same portal where we uploaded our answer sheets, or
That
we'll
I'm
get to know
not,
through
I don't
emails.
know. I'm not aware.
Okay, no
What is
problem.
the
No
portal
problem.
that you use to upload and all? I'm not aware. I think a detailed mail will come how to view those
Okay.
and apply for
So the general
revaluation.
practice is the
Ah,
evaluation sheets can be seen. Am I
yes,
right?
yes, yes. Yes. And what are the
Okay, that
constituent marks? And if there
okay.
are any remarks for those that what you have done right or wrong, that remarks also will be written. Okay.
Okay, that's good. Yeah, that's good.
So if
Yeah.
you feel anything is unfair, you can always apply for revaluation, and then the evaluator will reevaluate all those again. Okay, so it will be transparent. It will be the same for your end exam also.
Sure, sure.
There will be a revaluation window. So if you
Mhm.
feel that some unfair marks have been awarded, you can always apply for revaluation and then um, uh,
E-
get
Sure.
the appropriate marks. Yeah. I
So
don't
I
know
think
which
now,
portal and all that I am not aware.
no
Student
problem,
side.
no problem.
Yeah.
I was just curious that we will be able to see the answers. That was a good thing. That I
Yeah.
mean,
Yeah.
answers in the sense
It-
evaluated sheets.
yeah.
Yeah.
Yeah. It will be very transparent. It will be.
Okay, okay.
Yeah.
Thank you. Last one. Sorry for
No
bothering you
problem.
so
Please,
much.
please ask. Yeah.
So in now we are left out with hardly 5 sessions, excluding
So,
revision session, probably.
so 3 sessions are done, right? So I already started frequency response. I think we are
Correct,
on track. I
correct.
thought
So
I thought I
my
might need
question,
extra classes, but we are on
yeah,
track. Yeah.
sure, sure. My question is,
Uh-huh.
if we are able to get this watermarked exam material, that whatever you are
See,
teaching us,
I'll give that
little bit,
2 weeks before the exam. Okay.
okay, 2 weeks before the
2
exam.
weeks because
Okay,
you will have good amount of time to take the printouts and all. So don't
sure,
worry.
sure, sure.
Uh,
Yeah. So that would
so
help us. So
how will the watermark look like? I will try to show. So I took an advanced course. Yeah, this is so this is advanced mixed signal design. So yeah, no, not this one. Oh, not this one as well. Yes, better to always. So that one I taught for Wipro. So where is Wipro? Wipro. Advanced mixed signal design. Yeah. Just to give you a feel of how they look like.
Yeah, sure.
Material. So this is the consolidated PDF, I think, with watermarks. Yeah, this is 259 slides. Yeah, this is how they look like.
Okay.
So this is the
Yeah.
watermark. I'll give it.
Sure. Thank you. Thank you so much for patiently answering the questions.
Hello. Hello. Hello, sir. Am I audible? Hello.
Yeah, am I audible?
Yes, sir. Sir, I have also one query. Sir,
Yeah.
when you said like there will be lab exam, so this lab exam will be after 18th, right? When all our lab assignments will be done,
Yes. Preferably,
and it
yeah, after it.
will be
Think,
based on lab 3, 4, and 5, right?
that's it. Yeah. 3, 4, 5 or 4, 5. Let us make it between 4 and 5.
Okay. Okay, sir. Okay, understood. And it will be LT Spice based.
LT, that is why I cannot conduct a cadence based exam, right? We don't have so many licenses. Class
Right,
strength is
right.
above 120 or something.
Yes,
Because
yes.
the number of licenses are limited, we move towards LT Spice with the help of MATLAB.
Okay.
Yeah.
So, sir, like it will be in our lab class slot itself,
No, not lab
like it
class.
mean like
Typically we do
okay,
it in the night on any weekday. Okay, it is up to you. Whatever
oh,
you find 9 to 10 or 10 to 11 during any weekday. Okay, we don't even meet like this online class or something. I'll directly upload the question into Takshila portal. You have to submit the assignment like you do for your normal lab assignment. You have to do within that 1 hour.
okay,
Okay, I'll base it out of lab 4
oh,
and lab 5.
okay, understood,
Okay.
sir.
So I will
Thank you.
also conduct one
Thank you.
weekly quiz today after the class is done. Maybe by evening, I'll upload the weekly quiz as well on current mirrors. Okay. Is that fine? Or is it becoming too much? If something is too much, let me know. I'll can always have a discussion and reduce. Right. Yeah, I am done. I am tired also. You want anything? I am here. I am available. I can available for doubts. Yeah. If there is nothing, then you're free to go. I am available till 12:30 for doubts.
Sir, I have a question.
Please.
Sir, for open book exam, do we need to take only this PDF you have given, or
Yeah.
do we also need to take the textbook of any author like Razavi or someone?
It's better to take only the slides. I think you will have an orientation, proper orientation. What is allowed, what is not allowed.
Okay. Yes, thank you.
I will give the watermark slides 2 weeks before the exam. Okay. We will have ample time for the printing done. So don't worry.
Yes, sir. Okay.
Yeah.
Yeah, thank you very much, sir. Thank you for
Yeah.
answering all our questions.
Yeah, thank you. Thank you. Am I available till 12:30? Any doubts? I will be happy to.
Sure, much appreciated. Thank you so much.
Thank you, sir.
Thank you, sir. Yes. Thank you all. Thank you.
Thank you, sir.